Hello and welcome to RF Design Tutorials. This is tutorial 14 on advanced techniques of load pull simulation. Before we start, subscribe to my channel. Once you subscribe, click on the bell icon to enable all the notifications. And after you watch the video, don't forget to give it a thumbs up and share it with your friends and colleagues who may be interested in watching similar tutorial. I would like to pick up the thread from the last tutorial video on this topic. In the last tutorial, we understood the basics of load pull. How can you perform a simple load pull analysis in ADS, and then how do you decode the data which gets generated from the load pull analysis. In this video, we will extend our learning and go through some of the advanced stuff which you can do in load pull, and it's going to be very useful when you do power amplifier kind of designs. So let's directly dig in. Let us see what we did in the last tutorial video. Here we used a Cree device, and I used a resistor to stabilize the device, and I showed you how can you perform the parameter sweep by varying the row imaginary and the row real in the load connected at the output of this device. When we performed harmonic balance simulation, essentially ADS runs the parametric sweep, and then we are able to plot the contours by writing these two simple equations. Now, if you notice the P out dBm, which was one of our measurement equation in a schematic, we can very clearly see it's dependent on the value of imaginary component of row and the real component of row. And both of them are varying for 13 different points over the Smith chart. And the same has been depicted here with the black dots. So that's the reason where we perform the load pull and we got the analysis. Now, before we proceed, one of the users asked, how did I decide to set my load on a specific impedance, or how did I choose a particular zone in a Smith chart to run my load pull analysis? So let me quickly give that answer before we proceed. Now, usually the area where you may want to perform the load pull analysis can be done two ways. One, by referring to the data sheet, and here you can see I'm referring to the Cree data sheet of the part which I used in my analysis. Now in these data sheets, usually you will always find a section where vendor is describing the source and load impedances which are optimum for this transistor to produce a certain amount of power. However, whenever they do publish this kind of data, it's always extracted at a specific bias condition, and this load or source condition might change slightly depending on the bias condition you are using in your design. But it's a very good reference point, and here you can see it's very close to 20 ohm, which I used in my load pull simulation video, which I uploaded a few days ago. So that's one way of looking at it. The second way of looking at it, in case you do not have that information in the data sheet, remember the power devices which we are using, such as LD-MOS, gallium nitride, and so on, usually will always have the low impedance. So the region which you would like to check in a Smith chart would be around this area. And if you divide this circle on a quadrant, so usually it's the second quadrant area or the third quadrant area. That's where mostly you will find the most optimum conditions for your bias, for your load in the transistor. So you can always start with these two zones. But based on my experience, usually it's always the second quadrant where most of active devices such as LD-MOS or gallium nitride give you the desired impedance. All right, so hopefully this clears some basic confusion where to start performing your load. Now let's go and talk about little advanced stuff what you can do in load pull. Now for this purpose, I have a schematic here which is essentially the same what we used during the last video, but here the minor difference I would show is, we got our desired power during the last load pull analysis, but we don't know how the characteristics of this transistor is varying if I sweep the input power. And many times we may want to sweep frequency, Sometime we may want to sweep the bias voltage given to transistors and so on. Now these things can be very easily done in ADS. So here, for example, I have declared a variable called Pin and initialize it with certain value. In the harmonic balance controller under sweep tab, I am defining to sweep Pin variable from some start value to stop value in a specific step. Now this Pin variable eventually gets passed to the one tone source we are using. And here you can see I have passed in the Pin value. Now when we do that, basically the output power which we are going to calculate at this node will have three variable array, two variables as we had already seen before, and one more extra variable which will get added due to this pin. So let's perform a sweep and let's look at the data at the output. Now whenever we are doing this kind of sweep, we can have as many sweep variables as you want, and you can come up with a multi-dimensional data as you need. Now, before we look at the plots, if we go to the expression manager, and again, if you don't see this expression manager in new ADS version, you can always go to view menu and switch on expression manager, or just simply click E on your keyboard. Now here, if we click on Pout dBm, you can notice now it has a three dimensions, two as we had before, and the third dimension is Pin, which is corresponding to 55 sweep points, which are our input points. Now the equation which we used earlier has to be slightly modified, because if we want to plot contour on all the power on all the row, imaginary and real, you would virtually will not be able to make out anything from the contours. So that's why you can see the syntax. I'm using colon colon, which is wildcard, as I explained in one of my earlier tutorial video on multi-dimensional data sweep. And for the third dimension, I'm picking an index of the marker, and that marker I do have here on the slider. And to insert these kind of slider, again, I have explained in the previous tutorial videos. Otherwise, you can just simply go to insert slider and select Pin as the variable. And with the marker name, and in this case, my marker name is M7, which is plotted on Pin, I'm simply using this syntax here. So this allows me to filter out contours for the specified input power. And now if I change this slider here, you can see the contour information on the below Smith chart is changing with respect to the input power fed. So this allows us to have multi-dimensional data. Now, similarly, if you want to have more complex sweep, let's say along with sweeping power, you may also want to sweep the frequency of this source so that you can do a broadband power amplifier design. The step is very simple. Just add one more parameter sweep, define a variable which represents your frequency, sweep that frequency from some gigahertz to other gigahertz. And here, instead of giving it a static frequency, just go ahead and give the same variable name. And now when we do that, we will have four variables. And again, in data display, you could simply do the bit of data mining to have another slider of frequency, and you would be able to plot all the data as you require. Now again, the important thing which I wanted to bring into notice while I ran the simulation, notice here, this is the gain curve of power amplifier, and this is input versus output power curve. Notice, depending upon what reflection coefficient you pick for the load, you can see the output power is different and the gain, associated gain, is also different. Now, this is a very important aspect, and that's the reality, because your transistor is not going to give you a constant gain over all the load reflection, a region which you set. So while doing the PA design, when you perform this kind of load pull analysis, a lot of time you need to do this multiple sweeps to find out what reflection coefficient is giving you the best power, best possible gain, while not compressing your device into a deeper, compression level or in a saturation level. Now also you notice different load reflection points have different compression level. For example, while if you look at this trace, by the time you reach maximum power, you're already deep into compression. Whereas if you look at this load reflection point curve, you are not that much into deep compression levels. So this is an important thing to remember when you are doing those kind of sweeps, because sometimes if you push your device into 10 dB compression, 12 dB compression during load pull, you may see convergence error. So you need to take appropriate precautions while doing so. All right, so this is the basic fundamental of doing a bit of advanced load pull. Let's go and now talk about little more advanced stuff, which is going to be very useful for you if you are a power amplifier designer. Now to do so, I'm going back into ADS load pull design guide, and I would like to use some of the templates available. So here under load pull design guide, if you notice, there are many categories available, and I'm going to stick to the same one which we used last time. So here we used constant available source power last time. And here is the similar template to what I just showed you, which is swept available source power. When I activate the template, again, we see one data display like we saw in the last tutorial video, and then we see a circuit setup. Now, once you know the region in a Smith chart by step number one, when you ran the basic load pull, you know in which region you are going to get your desired output power. Now we can proceed to next step. And by doing this power sweep, you can define the sweep start range, stop range, and the step. And again, you can do these kind of sweeps in two levels. That means when your amplifier is operating in a linear region, you can go with little bigger step. And once you are nearing the compression, you can go for a finer, kind of step in your sweep. And that's precisely what it does. So I have already explained rest of the parameters in the previous video, so there is nothing much to mention here. But let's go ahead and run the simulation whereby we sweep, powers at different levels, and we would like to do a bit of data mining, because in the schematic and data display I just showed you, I could do some basic sweeps, I could do some basic, data mining. However, the template available in load pull design guide will give you much more information. So here you can see we have a similar slider where you can vary the available source power, that is the input power. And once you try changing the slider, you can see all the curves will automatically update based on what input power you are feeding. So this is pretty cool stuff, because you can get a lot of this information. Now again, this data display, if you look at the bottom, it has various tabs. And if you have switched on this page change, toolbar here, and you can do that very simply by right clicking and switching on the page. This allows you to flip into different pages. So here is another way of looking at the same data. And then you push forward, and again, you will have the regular data display, but here you can see you have the power swept data like what I showed you earlier in my simple schematic. And here the interesting thing, you can see the amount of data mining possible. Of course, you can set how many contours would you like to see and all that, like I explained during the last video. Here, while plotting contours, you can also see these purple dots, and those purple dots are the rows where your desired power is not satisfied. So in this example, we are looking at 29 dBm contour, looking at the gain contour and the compression level of the amplifier here. Now, similarly here, we do have a maximum PAE contours, and the points where you are not meeting the desired output power condition. Now the question is, who is deciding, where is this 29 dBm power? What if I'm doing 40 dBm, kind of amplifier, or 35 dBm amplifier? In the same template at the center, you do have a marker which you can set to do desired power delivered network, power delivered output. Now, similarly, if I switch this to 32 dBm, for example, the data will get updated based on 32 dBm output. And if you go back to the top level plot, you can see in the current configuration with the bias and input power sweep range, there are not many places where you are really going to get 32 dBm output. So the number of contours are pretty small. And here on the right hand side again, you can see the gain compression data and the gain data on a rectangular plot. So these fundamental, which I explained in the last video, is pretty much there. It's just that it has now multi-dimensional data on which it is doing number crunching. So it's very useful for you to design. Now the bottom section here basically is representing the load which is selected by marker M1, and that marker M1 is basically placed here. So when I change the marker in the region in which we ran the load pull, it keeps on updating and give you the latest updated information. So pretty useful. Now another thing which you would notice in the load pull design guide, when we go back and look at this circuit here, now there are few data displays which are dependent on this base simulation. Once you have this base simulation, you can click on the data display plots. You can see they are represented by this dash line. So once you run the fundamental simulation, now you can number crunch the data in different format. For example, if you would like to see contour at XdB compression, and you can define what is this XdB, whether it is 1 dB, 3 dB, and all that, you can simply select that data display template, click OK, give it some time because a lot of data has to be crunched, and now you will have a data display template where you would be able to see the XdB gain compression. Again, going back to the first page of this data display, you can see here is a slider which shows you data only corresponding to the level of gain compression which you would like to see. And here there are three performance variable. Performance one is PAE, two is gain, and three is power delivery. And here you have all the contours plotted for you to do the design. So this is efficiency, that's your gain, and that's your output power. And you can see different contours plotted. And again, depending upon, as I said, not all the data sweep points of load reflection coefficient is going to give you desired result. Here you can see some weird looking curve because at certain row imaginary or real axis, you are not getting any sensible data which is meeting the minimum criteria. And using these two sliders, you can limit the gamma in X. For example, I only want to plot from index number 2 to 9 by moving this slider. And now you can see these plots get updated only for the region of Smith chart where you wanted to do number crunch of data. So it's pretty useful in the sense that once you perform a sweep analysis with power, frequency, or your own desired parameter, you can use these data display templates to number crunch the data which you are looking for. This template is also very useful because if you are designing power amplifier for some modulated signal at a specific P out, you can observe ACPR as well as EVM contours. Now again, that data display has to do plenty of number crunching. So once you click on it, just be a little patient because the data display will come out with a bunch of data processing happening and you will have it in few seconds. So here is the data display with the ACPR and EVM contours. And again, as I said, there's a lot of data to be crunched behind the scenes. So once you click on that option, be a little patient. It will eventually come out depending on the processing power of your PC and how much RAM you have and what's to your CPU speed. Now again here, you can see you can set the desired main channel power, and depending on your selection, all the contours will be updated. And here you can see the ACPR contours, the EVM contour, and at the point where you are not meeting the output power. So meeting output power is the main criteria. And on that output power, you can look at various EVM level contours, ACPR contours, and then you have a bias current contour. So this is very useful, template also to look at. So tons of information available. Take your own time to slowly navigate your way through. It's not that during your amplifier design you may end up needing all the templates, but it is always good to know what all capabilities are available inside for designers to use. Now, one last thing which I would like to point it out before we end this tutorial video is in the load pull design guide, some of these templates may keep on changing depending upon which version of ADS you are using. So what I'm showing you belongs to ADS 2021 release. However, if you use ADS 2016, 2017 or any of the earlier version, you might not see all these templates available for you. So which kind of tells you that you need to update your ADS version. All right, so before we end the video, let me show you one more interesting simulation which we typically do, because in case of power amplifiers, it's not only about fundamental. How you terminate your harmonics is also going to affect your efficiency and output power. So in the same one-tone load pull simulation category, you do have a template here called load harmonic phase sweep. So once you activate that template, again, like earlier times, you will have a schematic and then you have a corresponding data display. Now you can set your criteria here, and notice in this case, I'm going to sweep harmonic number 2, which is second harmonic, because in PA design, second harmonic is the most important one to worry about. Not to say third harmonic is not important. So one by one you can sweep both second and third harmonic, and there are some new updates which are available where you can even sweep both second and third harmonic at the same time. Now here you can define the phase start and phase stop, and in degree of phase increment. Once we do that, the concept here is I have already run the fundamental load pull. I already know where is my output power coming, what's the input impedance. So basically, you terminate the transistor based on your source impedance and the load impedance, which you have already calculated. Now, under that PA operation condition, what we are trying to do here is to sweep the phase of second or third harmonic and see how the PA performance holds. Now, when we run the simulation again, a sweep simulation will be performed, as you can see here. So this is the condition where we can select the fundamental source with marker, and here is your S11 fundamental, right? So that's the load reflection coefficient fundamental, which we fixed where we are getting the desired amount of power. These red dots are the second harmonic phase condition. Now notice what is happening here. So this is your output power on the right y-axis and the power added efficiency on the left axis. Now when you have the x-axis as load, phase of your load reflection coefficient at 7 second harmonic, you can suddenly see at around this point, which is around 170 degree, is where your efficiency is going to drop, and also output power is seeing some level of drop. So while doing your impedance matching design, you may want to avoid the source, the reflection coefficient of 175 degree at the second harmonic. So whenever you do impedance matching network design, make sure you don't fall into this. Below this, your efficiency was kind of constant, output power was also constant. But if your second harmonic sees this phase, you are going to have a little bit of problem in your PA performance, right? So these are some of the advanced techniques of doing load pull simulations in ADS. I have one final load pull tutorial, which I'll be uploading soon. In that tutorial, I will show you how can you select loads on a Smith chart very, very easily. Because in this tutorial and the previous tutorial, we talked about selecting the right operating condition, and I have decided some area to sweep in terms of row imaginary or row real, or using the load pull instrument. We have selected it by either the Z or S load condition. But sometimes that gets confusing. However, the more straightforward method would be that I can look at the Smith chart and I can graphically select the region in which I would like to run load pull, and then ADS can just simply follow the region which I have selected graphically within the Smith chart. And it's not only constrained to a rectangular region or a circular region. I could have a pie-shaped region. I could have very arbitrary, region which is neither circular, not pie, not square. So all those interesting things I'm going to talk about in the next tutorial video. And you will also get a glimpse of the problem which we just discussed in this video is when you are sweeping the input power at various load reflection point, sometime at certain reflection, load reflection point, you might push your amplifier very deep into compression, causing convergence error. How can we avoid all those kind of situation? So stay tuned for next video. Hope you find this video very useful for your load pull simulation purposes. And don't forget to give it a thumbs up and subscribe to my channel if you haven't done so already. Thanks a lot for your attention.